guys, so I'm going to be going over what we covered last week now. So just to get started, we're going to go into antiderivatives. So I'm going to go over, this is the first problem on the, I think, November 21st handout, the one that we would have done Tuesday. So with these antiderivative initial value problems, you're trying to think of what function would give you whatever they're giving you as a derivative. So that's where the antiderivative comes in. Instead of deriving the function, you're kind of going backwards, which kind of, I guess, sneak peek, this is integration, but we want to, at the beginning, for you to think about it more as taking antiderivatives. So you realize you're learning still the same thing, it's just backwards. It's not anything completely new. So you shouldn't have to completely memorize all these new integration rules from scratch. So I would go ahead and simplify this function a bit. Instead of having the secant x multiplied by secant x tangent x, I go ahead and say this is secant squared x and secant tangent x. So if we think about now what function will give us this, well, first off we need to think about what function gives secant squared x as a derivative. And for that, it's just going to be tangent x, and then for secant x tangent x, it's just secant x. So I go ahead and give this as, I guess, my next step. Then from here, I guess notice I always add a c when I do these, because there can be some c that when I derive it ends up being equal to 0, right? And that's actually the point of these initial value problems, was we could actually solve for c given this initial value. So go ahead and plug in 0 into this sort of function, and then I get f of 0 is going to be tangent 0 plus secant of 0. And tangent of 0 is going to be equal to 0, and secant of 0 is going to be 1. So I get 1 plus c is equal to 3. So that means that my c has to be equal to 2, so I can go ahead and finish my function. And then this one is a pretty popular one with the initial value problems. In part, I guess these can be confusing because some people will forget, I guess, how you get from one to another. So I go ahead and say, to recall that acceleration is just the second derivative of your position function, or the first derivative of your velocity function. So when we're going backwards, we start at acceleration and try to think about what velocity function can be derived to get acceleration. So go ahead and put the work here for that. So for negative 32, it's just going to be negative 32t, and then plus some c that we don't know. And I guess I kind of do this one kind of quickly, because something you'll notice, they usually do this, is they'll give it as v of 0, and then you could kind of just automatically know that that is going to be your c. So for this one it's going to be 2, for this one it's going to be 5. You can go ahead and work it out like I did before on this one, where you actually plug in your values, but yeah, it's just going to end up being 0. So that's how you get to finally your position function. And I would probably on a test go ahead and circle both of these. And I do kind of specify C1 and C2. That's probably not super important, but it kind of just distincts, it gives some distinction between the two, so you're not getting those confused. And then moving on to Riemann sums. So I'm going to start off doing the first problem on the worksheet. Oh, and I guess I should have said, if you didn't notice, this is the last problem on the worksheet. The one from 4.9 that I just did. And then this one now is the, I guess, November 26th first problem. So the velocity of an object is given by v of t equals 1 over 5t over some time interval 1 is less than equal to t is less than equal to 7. One thing I'll just say now is the less than or equal to doesn't matter in antiderivatives, because there's not going to be any distinction between less than, or I should say, like, if it instead said 1 is less than t is less than 7, the answer would be exactly the same. anyways, we're doing this using 3 subintervals with left, right, and mid points is our like starting points. So I go ahead and give this graph here. In general with Riemann sums, I know you can't always visualize them, but I think it's good at the beginning to try to think about what you're actually doing with these Riemann sums. You're literally just approximating the area under this curve using these boxes. So if we think about this, I'm looking at my left endpoint. This isn't a very good approximation because we see at least like this chunk right here is way over approximating the area under this red curve. It gets a little better as things go on, but overall it's definitely going to be higher than what the true displacement is. And I go ahead and explain how I find these values, because sometimes it's not going to be these clean subintervals. So for this one, you might be able to just think about if you have 3 boxes where your left and right endpoints should be, but if you ever find yourself not able to do that, you can kind of go back to this equation. So I say for the width of each box, it's just going to be b minus a over n, where b is going to be this ending point, and a is going to be your starting point. And then your n, yeah, that's how you just get the width of each box. But that's also how you could count up. So you could start at 1 and then think, okay, 1 plus 2, I'm at 3, plus 2 more, I'm at 5, plus 2 more, I'm going to be at 7. And then left and right, so you're going to have, I guess, 4 numbers from that. And then for the left one, you pick the first 3, and for the right one, you pick the last 3, which I think I go ahead and say here. So if we look at our left one, we went ahead and picked 1, 3, and 5. And this width of each box, since we're taking the area, it's just going to be 2 times whatever the height of this is, which is obviously not to scale, because this is going to be 2 times 1/5, for example, for this box, which is this first part right here. And then for the next box, it's 2 times, said 1/15, and then finally we get 2 times 1 over 25. And it's perfectly fine to just leave your answer like this without actually trying to find some clean fraction. For the right, it's very similar, but instead we, as I guess I said, start from the left. So if you think each of these boxes, I guess some people get this confused as going the other way. Remember, you're still trying to approximate the area under this curve right here from 1 to 7. So now we're under, I guess, approximating that area. And it might be good at this point to try to think about what functions you're going to under-approximate or over-approximate based on whether you pick a right or left endpoint. Because there's some functions where it would be the other way around, where maybe it's going to be your left endpoint that estimates instead of your right. So I guess, again, looking at this, so instead for our first one we get v of 3, that gives us our height. Let's be that 1/15, which you can't really see here, but it is 1/15 times 2, our width, and then 1/25 times 2, still our width, and then 1/35 times 2, our width. And then lastly, the midpoint Riemann sum, you still can use these starting points, you just take the middle of those, which maybe is a little bit awkward. You could find your width and then count up half of whatever that is to try to think about those values, count up or down. Realize you're always going to have, however many subintervals you have, that should be however many of these points you should have, because you have 3 areas that you're calculating for 3 subintervals. And I go ahead and put these lines here to make it a little clearer where I'm getting these values from. So at v of 2, my height's going to be 1/10 or 0.1, and then I just multiply that by 2. Then at v of 4, it's just going to be 1/20 or 0.05 times 2, and then finally we get 1/30 times 2 for this final box. And that gives us our full displacement. And notice I'm trying to use the word displacement. I go ahead and use this again in the next problem to get you guys to maybe think about what this is meaning. What this is actually giving you is the change in position between 1 and 7. So how much you've moved over that point. So I guess like before, remember when we were taking these antiderivatives, we had to have a plus c because there was some arbitrary other value that we didn't know. When we're taking Riemann sums, or you'll see definite integrals, you don't need to worry about that c, because in essence that kind of gets left behind. Because think about if we have something like maybe your displacement over a certain amount of time, it doesn't matter where you start, right? Like if we define Fayetteville to be 10 and Bentonville to be 30, and I just want to know how far you've traveled, it would just be 20. It did, but I guess it more so mattered the distance traveled over that time, not where you started, so to speak. I think that was a bit of a convoluted way of explaining that, but maybe it'll become a little bit more apparent in the next bit. Okay, so I start off with, this is one of these definite integrals using geometry. Now this one's a bit of a maybe simple function. I'm just saying v of t is equal to 5. But I go ahead and define it as meters per second since it's velocity. So I guess first off, let's just think about if I told you that some object was moving 5 meters per second, and I wanted you to know the displacement between 5 and 10 seconds, how would you calculate that? And it wouldn't matter to you what you defined as, I guess, the origin in this case, because all you're worried about is between 5 and 10, how far it traveled. And that amount that it traveled is just going to be that velocity times the 5 seconds. And I guess I even say, since it's constant, you don't really care that it's between 5 and 10 seconds. I could have said it was between 4 and 9 seconds, or any other bit that was 5 seconds long. It would still be the same answer of 25 meters. Similarly, if I asked you the displacement between like 9 and 10, it would just be 5 meters. It would be the same as how long you traveled in 1 second. But another way to think about this is taking the area under this curve. So the area under this curve, well, it's just going to be my time, which is given by this, and then my velocity is given by my y-axis. So over 5 seconds, I traveled 5 meters. So 5 times 5 is going to be 25. And then I go ahead and say here, I could also think of this as my change in s, my change in position, between 10 and 5 is 25 meters. Yeah. So I guess what I'm getting at here is we are still taking an integral. It'll become, I think, more apparent this week how. So now I have a slightly more complicated function. This one's pretty similar to, I think, maybe no, not number 1. I think it's the first one they give you using geometry, so maybe number 3 or something on the worksheet. But it's defined by t over 2 plus 1 meters per second to determine the displacement over 5 is less than t is less than 10 seconds. This is one where I couldn't really do it in my head, I don't think. I wouldn't be able to figure out from that information without doing a little bit of math. Now, I would probably not calculate it this way, but if you don't know any calculus, you can calculate it this way. So displacement is still going to be just this area under the curve, which, since this curve's geometrically pretty simple to calculate, we could just use geometry. So how I did this, I went ahead and broke this up into my like 2 sort of shapes, because I have a triangle here and I have a box. So this first one here, this 3.5 times 5 is that box. So if I go starting at 5 up to this point, that's going to be 3.5, and then my width of this box is 5, so that's where I get that area. And then I kind of start at that point, go up to the top, It's going to be 3.5 up to 6. So that's going to be 2.5, and still times 5, but since it's a triangle, it's going to be 1/2 base times height. So that's where you get that 2.5 times 5 times a 0.5. And then total I get this 23.75 meters. So I guess that's pretty much it for this section. I guess, as I said, just wanted to try to put some of this information in a different way. So yeah, that's all for this week's